coordinates to explore solution spaces. A talk for the GECCO visualization workshop. My name is Neil Urquhart. I am a lecturer in computing science at Edinburgh Napier University. I'm interested in evolutionary algorithms, evolutionary computing in general. I'm particularly interested in how evolutionary computing can be applied to real-world applications, real-world scenarios, and the way in which the concept of evolving an answer can potentially match far better to real-world scenarios than some more traditional methods of optimization. The area that I have a particular interest in at the moment is probably best described as urban logistics. How we deliver goods and services within towns and cities. It's a very interesting area because not only is there a lot of hard optimization in terms of building routes, allocating deliveries to vehicles or people, there's a lot of soft constraints as well. Trying to meet aspirational constraints about reducing costs, about reducing congestion, about reducing emissions, and dealing with very real constraints, dealing with limited resources and deadlines. I wouldn't describe myself fundamentally as a visualization researcher. Really, if truth be told, I've never been terribly interested in visualization. It's something I have tended to get problems, to solve them, to present my results in a way that the user can understand and move on. However, I have in recent times, as I began to work with Illumination algorithms, come to the conclusion that there is an awful lot that good visualization can give us. And so this talk is all about how, when solving many objective problems, we can use an Illumination algorithm, and how we can use visualization to help the user get the most from the visualization algorithm. And the combination of a visualization algorithm and parallel coordinates visualization really seems to give us a very, very promising technique for such problems. Optimization. So let's go back and just revise what we mean by optimization, or certainly what I mean by optimization. Single objective optimization to me is characterized by the good old travelling salesman problem. Just on the off chance that anybody doesn't remember what travelling salesman problem is, essentially a salesman has to visit a set of cities. They must visit each city once, no more, no less. The optimized solution is a solution that allows the salesman to make the visits, visiting each city once, no more, no less, in the shortest possible distance. And here we have a rather nice example. This is an example of one of the few real-world practical applications of travelling salesman. It's the travelling Santa Claus problem. Santa Claus commences from his grotto in the frozen north and travels around the world, visiting cities before ending up back at the grotto. In this single objective environment, there is only one solution. There's only one objective to deal with, which is get the distance as low as possible so there is only one answer comes back. In the world of single objective optimization, things are quite simple. But most real-world problems, in fact, are what we would call multiple objective. There is more than one thing to optimize. The solution has more than one objective, one characteristic. One of the ways in which scientists began to solve multi-objective problems was in fact to turn them into a single objective problem. So they could work in this environment where the user presented a problem instance and the algorithm presented back the solution. No user choice whatsoever. One way this was achieved was by combining multiple objectives into one fitness value, by multiplying them each objective score by a weight. The weight, to some extent, represents the relative importance of that objective. But here's the problem. Who decides on the weights? If the weights have to be decided on and are incorporated within the program code, then they have to be decided on at the time of development. If the weights can be optimized through a configuration file, how do you train users to do it? Can a domain expert really be trained to optimize the weights? So it's turning a multiple objective problem to a single objective problem in this way doesn't really solve many problems. Moving on from single objective problems, we have bi-objective problems, bi-objective optimizations, where we have two objectives. So in our area of logistics, our two objectives might be emissions versus cost. And it may be that these objectives may be complementary. If we reduce one, the other one reduces, or they may be conflicting. If we reduce one, the other one increases. Where our two objectives are complementary, we can simply focus on one objective, reduce it, and the other one will come down. Where they are conflicting, as they are in many situations, we reduce one, the other one increases. Where we have two conflicting objectives, so suppose our objectives were cost, the cost of providing deliveries versus the CO2 produced, the environmental footprint. Now it may be that the lowest cost solutions involve putting all the deliveries in one big van, having one person make the deliveries using a van. That is quick, only requires one employee to do lots and lots of deliveries, but it produces a lot more pollution. If we use walking couriers or cargo bikes, that's more expensive in terms of our daily wage bill. We need far more people to do it, but it's far more environmentally friendly. So we have options. We can find a solution that optimizes X at the expense of Y. It basically optimizes on cost or emissions. We can find a solution that optimizes Y at the expense of X. Or we can find a solution that optimizes Y and X so that neither is optimal, but both are acceptable to the user. This is referred to as a trade-off. Finding a solution that is within our cost budget, but also meets our aspirations to be environmentally friendly. The problem with trade-offs are who makes the decision as to how we should, for argument's sake, trade off environmental impact versus cost. That is a very politically charged decision, a very emotional decision, in fact. And it's not necessarily a decision that is best left to an algorithm. It is probably ultimately a decision that is best undertaken by a domain expert. One of the approaches that we can take is to use our optimization algorithms to produce not a single solution, as we might do for travelling salesmen, but a set of solutions that illustrate the breadth of choice available to the end user and then support the end user in making that final choice. And it is in making the final choice that visualization can assist us. Within optimization, bi-objective optimization and multi-objective optimization, one of the things that we can look at, one of the techniques we can use is that of Pareto Dominance. Pareto Dominance was a concept established by Vilfredo Pareto, 1848 to 1923, who was an Italian economist, engineer and grower of beards. Pareto Dominance allows us to look at two solutions and establish if one solution is said to dominate the other. If a solution dominates the other, then it basically says there is no reason why you would choose the dominated solution over the non-dominated solution. What does that mean? Well, we've got two solutions, X and Y. X dominates Y if X is no worse than Y in each objectives and it's better than Y in at least one objective. So one of the things we can do is to create a set of non-dominated solutions. Rather than running our optimizer to produce a single solution, we can say here's a set of non-dominated solutions. As soon as we have more than one objective, we can produce this set of non-dominated solutions. This set is known, sometimes it's incorrectly referred to as a Pareto front, it's more correctly known as a non-dominated front. The reason being that for a given problem, the Pareto front is the best set of non-dominated solutions that can be found ever, the optimal set if you like, whereas a non-dominated front is simply a set of solutions that are themselves non-dominated. When we run something like an evolutionary algorithm, we need to be careful because unless we can prove that there are no better solutions out there, we haven't found a Pareto front, we've found a non-dominated front. And it's a bit nitpicking, and the reason why I mention it here today is because when I first started playing with this stuff a few years ago, one of the first conference papers I wrote, one of my reviewers very kindly took the time in a review to explain that subtlety and mention it and say, stop saying you've found a Pareto front because you can't prove you've found a Pareto front, you've only found a non-dominated front. And they're quite right. This talk is not going to spend a lot of time looking at optimization methods since we're here today to talk about visualization, but to give an example, if you're interested in finding non-dominated fronts, NSGA2 and indeed now NSGA3 are the algorithms you want to look at from the point of view of taking a problem and optimizing it. A very good paper looking at a real-world application, a practical application by Beatrice Ombuki et al. 2006 for looks at vehicle routing, and I think indeed it was garbage collection that we're looking at. Have a look at the Ombuki papers. They will give you an example of how to write a comparatively simple evolutionary algorithm which uses dominance. The great thing about evolutionary algorithms is that if you look at the internals of how an evolutionary algorithm works, Pareto dominance works rather well. We select two solutions at random. If one solution dominates the other, that solution is selected to become a parent. When we want to replace something, we can select two solutions. We can select a solution, if a child dominates this solution, we can replace it. We can use very easily the dominance operator for our selection and replacement. So Pareto Dominance fits in beautifully with evolutionary methods. The NSGA2 algorithm is a particularly nice algorithm, quite a complex algorithm. It looks not only at dominance, but it also tries to find a non-dominated front which has solutions spread along it. But let's have a look at a front. So here we have a visualization in 2D of a bunch of solutions to a fictional logistics problem, and we are looking at cost and environmental impact. We've evolved this set of solutions, and because they're 2D, we can plot them very easily on a bit of paper. If we look at A, pick solution A, everything in that sort of ready highlighted area is dominated by A. A is better than these three solutions in at least one way and equal to them in every other way. There is no reason why I would pick any of these three solutions over A, apparently. If we go through these solutions, we can create this front of non-dominated solutions where the solutions highlighted by the polyline are those solutions that are not themselves dominated. It is that front of solutions, the NSGA2 or the techniques described by Umbuke will give you. And what we are trying to do now is use our evolutionary algorithm to get this non-dominated front as close towards zero as possible. So get the middle part of the front, as close towards that theoretical bottom corner where we would love to be. And what we are hoping to do is to find as many solutions as possible to populate that front, because the more solutions we find on our front, the more choice we can offer the user. Ideally, it would be nice to be in a situation where we could find solutions that map to almost every point on the axes, so that a user can say, if I pick, we can present a user with an interface that effectively gives them two sliders, one of which environmental impact, one of which is cost. You pick where you want to be on one, and it shows you where you are on the other. At the moment, with this particular solution, there are 6 points. So I've got 6 costs, 6 environmental impact points. I pick one, I see what I get in the other solution. Pareto dominance can in fact be implied in many dimensions. The problem is that above 2D visualization becomes difficult. 3D is possible. You can easily generate 3D plots in MATLAB, which look really impressive, absolutely fantastic. They will impress your friends and relatives, but actually, choosing a solution from them is remarkably difficult. Giving a domain expert rather than a data scientist or a computer scientist a 3D plot and say pick your solution from that is almost invariably going to confuse them. And once we get above three dimensions, once we get into problems which have more than 3 solution characteristics, plotting becomes very, very difficult indeed. But there is an answer. The parallel coordinates plot. And the main part of this talk is on why parallel coordinates forms a fantastic means of visualization, and in particular how we can combine it with Illumination algorithms to create a very powerful technique. So just to whet your appetite, here is a parallel coordinates plot. We have 4 dimensions, 4 objectives, A, B, C, D. Every solution has each of these 4 characteristics. So any solution can be drawn on this chart using a polyline, such as a green polyline, that intersects each of these axes at the appropriate point. Parallel coordinates. A look on the internet suggests that parallel coordinates in some format have been around for really quite a long time. However, the use of parallel coordinates as a plot for showing multidimensional spaces is really down to the work of Alfred Inselberg, and in particular his book Parallel Coordinates, Visual Multidimensional Geometry and its Applications. I would really recommend the book. It's very, very readable, and it will really teach you everything you've ever wanted to know about parallel coordinates. If you find them at all useful, take the time to read this work. So, the basic principles of a parallel coordinates plot. Each solution that we want to plot, so each of our solutions is a polyline, and each of these polylines intersects the axes at the appropriate points. So where we have an archive of solutions, we get a plot like this where we can see a whole bunch of lines there. The power of parallel coordinates lies not just in the presentation, but in the ability to interact with the plot. And we'll come to tools later on, but the majority of parallel coordinates tools allow some form of interaction. One of the most useful forms of interaction is that of brushing. Brushing simply allows you to highlight a particular area on one or more axes. So in this case, we have our 4 axes for this particular problem, and we're interested in finding solutions that have a low cost per bag, a low delivery cost for each bag of groceries delivered. In this case, we use the brushing action to highlight this area here of the axis, and we only show the solutions that pass through this highlighted area. And the power of this is that this brushing technique allows us to use parallel coordinates to answer questions, in particular to help us find solutions, to help the end user find a solution that meets the requirements. Remember the requirements we talked about earlier on, where we said, particularly in our area of urban logistics, there are many conflicting requirements. The user may have many differing pressures put upon them. In that environment, it's desirable to try to find a very particular solution. So in this case, we have a very simple urban logistics problem, and solutions are characterized by the distance covered, the time it takes to make the deliveries, the cost for each bag of groceries delivered, and the number of individual routes required. So we might say to the question, find me a solution that gives me a low cost per bag, but also prioritizes delivery times. So using the brushing technique, we first of all brush down on cost per bag, so we highlight only those solutions that intersect the cost bag axis at a low point, and then we bring down time. And as we bring it down, what we're looking for is the polyline that intersects through the cost area that we can afford and has the lowest possible time. This ability to answer questions is what makes parallel coordinates so powerful. And as we'll see, when you combine this with an illumination algorithm, it allows a user to ask for a very specific solution. The other thing we should look at here are the relationship between the axes. So the vertical axes, as we will recall, each represent one particular problem objective or dimension. And by looking at the shape of the chart, by looking at the shape made by the polylines, so we can very quickly establish the fundamental relationship between axes. So if we look at the relationship between cost bag and routes, that is a complementary relationship. We know that because we see the lines between them are basically horizontal. Distance and time, however, we see that most of the lines go at an angle and cross in the middle, so we see that that is a more opposed relationship. Most parallel coordinates tools will allow you to rearrange axes by dragging in order to put particular axes next to one another in order to see the relationship between them. Illumination algorithms. So by using algorithms based on Pareto optimality, we can generate a non-dominated front that gives the user some choice. But what about giving the user more choice? What about giving the user choice that represents the entire solution space? So the idea behind an illumination algorithm is to, in effect, illuminate the solution space by finding a representative set of solutions that demonstrate the possibilities available across the solution space. The algorithm that we're going to look at here, and the one that I have used quite extensively, is MapElites, which is a map of phenotypic elites. And it was first described by Murray and Clune, 2015. It's been used in a number of areas. It was initially used to help evolve robots, to evolve diverse populations of robots with slightly different characteristics. It was used by myself and Emma Hart to tackle some urban logistics problems. And we were certainly the first people to use the technique in an area other than robotics. So let's start off with a logistics problem that has two objectives. Keep life nice and simple. We have financial cost C, environmental impact E. Suppose we evolve the following solutions to our problem. And because this is a two-dimensional problem, so we can plot this very easily in 2 dimensions. Now, if we happen to know that the maximum and minimum values for C and E are 350, 650, and 950, 1140, then the number of possible solutions would be 57,000. So what we could do, if we want to give the user choice, is simply start to build up a collection of all 57,000 solutions, and then allow the user to browse through it. That idea, however, has a number of practical considerations. The resources required to maintain a data structure of 57,000 solutions may impose a severe runtime overhead in our software. Many of these 57,000 solutions may not in fact be themselves valid solutions. Many of the solutions may be very similar to other solutions and may not be significantly different from many other solutions. So why would you why would you maintain a data structure with solutions that are either potentially not valid or not distinct from other solutions? It's also worth remembering this is 57,000 solutions for a very simple 2-dimensional problem. the solution space increases dramatically as the number of dimensions increases. And remember the area we're in, the area of urban logistics, we've already talked about the fact that within that area there are potentially many, many dimensions to a solution. MapElites seeks to create an archive which contains a set of solutions, and that set of solutions should be representative of what is available across the solution space. It's not every single solution. The hope being that if we pick a representative set of solutions, we don't have so many solutions that are either not statistically different than neighbours, and of course we don't have solutions that are not valid. What we do is MapElites divides a solution space into a series of buckets, a series of areas within the solution space, and we seek to find a solution for each area. By only finding one solution for each area, so we reduced overall the number of solutions in our archive, but also we don't find solutions that are very similar to one another. There is a definite trade-off in all this between the number of solutions that we put in an archive, and it's that number that gives us powerful choice, versus the practicalities of having a smaller archive which is more manageable. In this case, what we do, MapElites scales each solution characteristic into a smaller range. So in this case, we could scale our 2 objective into the range 1 to 20. And that then means that we have an archive size of 400 solutions, which represent our elites. So the archive can be looked at as having 400 empty spaces or empty buckets, each of which can contain a solution. One of the things that we have to do in MapElites is to translate any raw value for a particular objective into the scaled value. Right? Not especially difficult to do. The main thing is that you need to know what the maximum and minimum values of that objective are likely to be. That can cause some interesting moments trying to establish that. How do you know the minimum value of that an objective can reach unless you've exhaustively solved a problem? The answer is you potentially can't. In some cases, knowledge of the problem domain will tell us that we can reduce a particular value to 0. In other cases, this simply has to be a good estimate. We have our minimum value, our maximum value. Maximum values are easier. What I've done is in the past is I have just created a bunch of random solutions and taken the maximum value as being the average value found when generating a number of random solutions. I'm not interested in anything that's worse than random. However, care is required when selecting these values. A detailed discussion, though, is really outside the scope of this particular talk. Suffice to say, it becomes necessary to establish the likely maximum and minimum of each objective. Once we know that, we can then map our objectives onto a scale, in this case a scale of 20. So now we have our set of 4 solutions, and we can now map them each to a bucket. So we can now have each of these solutions occupying one bucket in our archive. Each bucket in the archive actually represents quite a large area of the search space. And of course, it is going to happen that as we evolve solutions, so as we use mutation and cross over to evolve solutions, at some point we will end up evolving a solution that maps to a bucket that is already occupied. What do we do when two solutions wish to occupy the same bucket? What we need, therefore, is, within the MapElites scheme, an overall fitness value. Another solution characteristic on top of the ones that we already have that helps us determine which solution occupies a contested bucket. In the case of the logistics type problems, I normally use overall distance travelled as a fitness measure, on the basis that in almost any solution, in almost any other metric, reducing the overall distance travelled in a solution almost invariably improves the quality of the solution. So in this case, best fitness value claims occupancy of the bucket. The problem with MapElites is that archives become very large very quickly. You very soon find you are producing archives with hundreds, even thousands of solutions. When I first used this technique on a logistics problem, I was working with a colleague whose background was not computing, but they were a transport planner. And they said, "Why have you done this? All you have done is you've taken a problem that I can't solve because the number of solutions is too large. You've run your software, and instead of having, 1 billion possible solutions, you're now giving me a couple of thousand." At the practical level, it's as difficult to look through a couple of thousand solutions quickly and pick one as it is to look through 1 billion solutions. You haven't solved a problem. At that point, it became apparent that what was needed was some means of helping a domain expert visualize the archive and work through the solutions in the archive. The problem, of course, presents a solution, and it's a solution that most of you will probably have already realized. We use parallel coordinates to visualize the archive. So let's take a case study. So this is a case study. This isn't a case study that's been published yet, but it's a nice generic, simple to understand case study. We have a supermarket. Supermarket offers a home delivery service. Customers place orders online and they have them delivered the following day. At the start of each day, the supermarket manager has to pick and determine a solution that will be used that day for making the deliveries. And our supermarket has a mixture of conventional vehicles, vans, and low-emission cargo bikes which are used to perform deliveries. A plan has to make use of some vans, some cargo bikes in order to undertake that day's work. And within our supermarket, we identify a whole bunch of characteristics that are of interest to us when considering a solution. The total daily fixed cost. The total fixed cost of using the vehicles that we're using that day. The total staff cost. The cost of paying the bicycle riders and the van drivers to undertake that work, particularly if they're paid by the hour. The vehicle running costs. The cost per delivery, per bag of groceries delivered. The emissions produced that day by the delivery activities. The percentage of deliveries made by bike. The percentage of the distance covered that day by bike. The number of bicycles required, which of course also relates to the number of riders required for these bicycles, and the number of vans required that day. All of these things have to be considered by the manager when they are planning and choosing a solution. We create some problem instances, and we use previously published instances by Urquhart. And then we model some costs. So we have capacities, fixed costs per day, cost per kilometres, staff cost per hour, loading time, speed and emissions for both modes. So any particular solution, we can use this model for the two transport modes to work out how it will perform in relation to the 9 characteristics. But let's think of this from the perspective of the manager, the domain expert, the user, the person who uses the output of our optimization. Each day, the manager has to pick a solution that will be used that day. The choice will be governed by constraints, things that must be met, and aspirations, things which should be met. From the manager's perspective, some of these constraints may not appear until the day of the deliveries. They may appear very much at the last minute. There may be a sudden change in the weather. There may be a sudden non-availability of staff. There may be a sudden non-availability of vehicles. Example constraints and aspirations that might affect our manager when they are choosing the solutions. Constraint, staff shortage, only 4 bicycles can be operated. Constraint, vehicle shortage, only 2 vans are available. Constraint, weather emergency, no bicycles can be used. Ice is formed on the ground, unexpectedly, no bicycles will be sent out. All of these things are hard constraints that have got to be taken into account. Aspirations. The manager is part of a larger organisation. That organisation has aspirations. Reduce the delivery cost. Keep the cost down. Reduce the staff cost. Reduce running costs. Aspiration, make the maximum use of cycle couriers for publicity purposes. Reduce fixed vehicle costs as much as possible. All these are aspirations which in a big organisation can come from different parts of the organisation in order to meet different and often conflicting objectives. The choice of the final solution is not only a very complicated choice, but it's also a choice that's actually got to be made rather quickly. In the on-demand economy, where we expect to order things and have them delivered quickly, choices have to be made rapidly. So, we run our MapElites algorithm. We evolve an archive of solutions. We have there our 9 problem characteristics. And we build a parallel coordinates chart for a particular run. This run has several thousand solutions in the archive. And this is what we get back. It's a very, very impressive plot. Some people have even gone so far as to say that if you look at it for long enough, you will see some sort of modern art in there. But so far, it is of no use to our manager. So far, we have no filters, no brushing has been applied. We haven't really started to use any of our constraints or aspirations to find a solution. But somewhere on that chart is probably the solution that we want today to meet the aspirations and satisfy the constraints that we have right now. We have to apply the constraint, vehicle shortage, only 2 vans available. Straight away we use the brushing technique on the van's axis and we bring it down to the maximum of 2. Suddenly we only see those solutions with 2 vans. Suddenly we see straight away that if we're going to use 2 vans, we need to make far more use of cycles. We find out if we're only going to use 2 vans, we're going to meet our green credentials, our emissions are going to drop. Our staff costs are going to go up. Why? Because bicycles have a smaller capacity, therefore we need more cyclists, more staff to ride them. Our costs drop down nicely because bicycles are cheap. Straight away, we have suddenly taken that big archive, that big green messy spaghetti-like blob, and we've used that very simple brushing technique to apply one of our constraints. And suppose that along with that we have an aspiration that says reduce the costs. Like any organisation, reduce your staff costs, reduce your running costs. So now what we do is we start to bring down, using the brushing mechanism, we bring down staff costs and running costs, and we bring them down as low as we can till we find a solution that only has our 2 vans and has staff and vehicle costs as low as possible. By using the parallel coordinates visualization, our manager has been able to find that one solution in that big green horrible mass of solutions. The one solution out of the thousands in that archive that will fit them for the problems they have that day. Now, something to remember is that because we've used an Illumination algorithm, we can have had the software, the optimization algorithm, running if necessary for several hours, running all night, filling up this archive. When the manager learns about the constraints the next day, when they're trying to find that problem, they're not rerunning this, they are simply using the visualization tool, and as we'll see when we demonstrate some of these tools in a few minutes, it's all basically happening in real time. They're moving sliders up and down the axis to filter solutions, and they're doing it quickly in real time. So finally, what tools are out there for you to use? So there is the Elite Visualization, or ELVIS tool, which is available online. It will take a CSV file which contains a list of solutions and generate an interactive parallel coordinates and heat map plot for each one. There's Xdot. Xdot is the tool that I use for creating the screenshots in this talk. It's a particularly nice tool. It's written in Java, so it will run on just about anything, Windows, Mac, Linux. Very simple to use, produces very nice interactive plots. If, of course, you're building your own optimization tool, there are plenty of other libraries, which including various JavaScript libraries which support parallel coordinates, so you can easily incorporate them without too much work into your existing software. And that brings us towards the end of our talk. So some conclusions, and these are frankly my opinions. In this context, user choice is best supported through visualization. Parallel coordinates are intuitive visualization techniques that domain experts can understand. I've shown parallel coordinates plots to people, domain experts in transportation, in logistics. I've shown it to people who work in our local authority in Edinburgh, as well as those who perhaps work for charities, who are coordinating volunteers making deliveries. And in just about every case, there was an intuitive understanding of the parallel coordinates plot. It's not enough just to paint a picture, it has to be interactive. The real power of parallel coordinates is not just that big green blob, but it's the ability to use the brushing action to narrow the area of interest on the axis in order to highlight specific solutions. Thank you very much to all my colleagues at Edinburgh Napier, also colleagues at Technical Hoxton School Mittelhessen, who I've worked with as well over the years, and they have all encouraged, criticised and motivated me towards this work. Quick shameless advertisement. A lot of what's been in this talk will be appearing in a book provisionally entitled Evolutionary Vehicle Reading and Logistics from Theory to the Real World, which is due to be published by Springer later this year, and indeed it would form an ideal Christmas present for any data scientists or computer scientists that you know. Finally, at the end of all this, any questions?